I tend to not stress target material and the differences in output and technique compensation for changes in target material, not because it's insignificant, it's extremely significant. The, uh, the, the type of target that we use is going to affect everything except for the maximum and minimum energies. So again, the things that affect maximum and minimum energies are the amount of kinetic energy that we can lose, and that's determined by the speed of the electrons, and that's determined by the potential difference of the kVp that we apply to the X-ray tube. Minimum energy is controlled by the amount of filtration, but everything else, including the characteristic spectrum, is going to be different for different types of target material. The reason I don't stress it is, and the reason I don't go into things like technique compensation, differences in output, and specifics like that, is because it's not something that has appeared on the registry as of yet. If there ever comes time that we have to calculate technique compensation for changes from molybdenum to tungsten targets, then I'll incorporate that into the lecture. But it's just not something, it's not a penguin, to put it in Bouchon terms. It's not a penguin that you need to clutter your mind with, so we don't really talk about it too much. So target materials change everything except for peak and minimum energies. The differences in target materials are always going to be lower atomic number than tungsten, and where we use those are in mammography. So the lower atomic numbers, because the nucleus is smaller, it's harder to get the projectile electrons close enough to the nucleus to get high energy brims. So it's not necessarily harder to get brims, it's harder to get high energy brims. So there's always a change in the appearance of the brim spectrum. There's always a lower output, and the characteristic spectrum is going to be different because it's a different atomic number. So those inner shell binding electrons are going to exist at different energy levels. So characteristic spectrum is different. We get a decrease in output, and the averages are going to be totally different. So technique compensation, yeah, you'd have to use probably quite a bit more mass in order to make an exposure off a molybdenum target, but you're never going to run into it, so you're not going to be tested on it here. You're not going to be tested on it on the registry. I'm going to play this video, and if the audio doesn't play, I'll post the link to the video into the module so that you don't have to copy and, or not copy and paste it, but you don't have to type it in. But this is a video showing the interactions inside of the patient's body. So this video is pretty technical, but what it bubbles down to is this, that as the X-ray beam enters the patient's body, first off, we have a tendency to think that X-rays um, get filtered out by the air, and that's just not true, and it's not a practical way to be thinking about X-rays. So air doesn't really filter out any X-rays, but anything that it passes through that has a semi-solid medium to it does. So soft tissue absorbs a lot of X-rays. Bone absorbs exponentially more X-rays. So the thicker the body tissue, the more X-rays that you're going to absorb. Now notice though that it's not linear, so it doesn't just go straight down. It kind of evens out a little bit. And the reason for that is for the same reason that filtration hardens the X-ray beam. Basically, the patient's body filters out some of the X-rays so that you get to a point of diminishing returns. And I use that almost in a reverse capacity, so that at some point your X-ray beam becomes so almost filtered by the patient's body that additional soft tissue doesn't do quite as much as what you would think that the initial soft tissue would. In other words, you notice that the first portion here is a little bit more steep than what it is down here. So you've got this inverted bell curve. And in bone, you've kind of got the same thing, almost to the point where it flattens out right before you get total absorption of the X-ray beam. But you don't get to that total absorption in soft tissue because, again, at some point, those low energy photons are going to be absorbed into the patient's body. Now, bring all this up because we're going to talk about technique compensation for patient size. Now, I know the techs that you work with have a tendency whenever they have a patient who is a hypersthenic patient versus an asthenic patient, have a tendency to increase their KVP. And you're probably going to do the same thing. I did the same thing. And if I went back into clinical practice now, I probably would do the same thing again. But if you have a hypersthenic patient, right after you have an asthenic patient, what you'll see is the technologist will increase the KVP in a lot of cases. It's not necessary, and the literature says that you should not increase KVP because as you increase KVP, you increase the scatter radiation. And because a hypersthenic patient is hypersthenic mainly because of soft tissue, and it increases soft tissue, and soft tissue casts more scatter radiation than what bone does or air does, that you're compounding the problem by increasing KVP. So you should not increase KVP. I'm just pointing out in clinical practice that even though the literature says don't increase KVP, you're going to see a lot of people increasing KVP. But it's truly not necessary. But if you don't increase KVP, you're going to have to increase mass pretty substantially from an asthenic to a hypersthenic patient.
Tissues and bone. All right, so we need, at any given distance x, we need a difference in the intensity. And obviously, that the X-rays will decrease much quicker with distance. All right, and that's what we want really, because we want to see a difference between soft tissues and bone. All right, so we need, at any given distance x, we need a difference in the intensity. And obviously, that will show up as different shades on the X-ray photograph. All right, so bone is a better absorber of X-rays. The decay is much quicker, and therefore it has a higher absorption coefficient. All right, so something with a higher absorption coefficient mu means it's a better absorber of X-rays. It's not quite as simple as that because it also depends on the energy of the incident X-ray photons. Right, and we'll have a look at how that works in a minute. Now, the unit of the attenuation coefficient is per meter. All right, just meters to the -1. Okay, now we've got back a little bit. We skipped over this question, basically because it was in the wrong place in the slides. So there's a little question here which you can have a go at, and if you pause the video for a moment while you do that, and then if you've got any problems, we'll go through it in lesson. Okay, so here are some typical absorption coefficients for bone and muscle, and this is quite interesting because you can see how it depends on the energy of the X-rays. So up here we've got very, very high energy, very high frequency X-rays, 4 mega electron volts, and that's pretty much the highest we can produce in X-ray tubes, going all the way down to about 50 keV. And you can see that as the X-ray energies go down, the absorption coefficients for bone and for muscle both increase. Okay, bone and muscle is better at absorbing X-rays, i.e. it absorbs low energy X-rays much better than it does high energy X-rays.
So I wanted to stop on this slide and point out a couple of things. This is the absorption coefficient of bone and muscle as we change voltages. So 50 keV, 50 kVp is basically what we're looking at here, and that would be maybe a finger technique as opposed to 4 milli electron volts, and that would be pretty close to a therapy type dose. Now, if you notice, your absorption coefficient at low kVp is quite different. So it's 0.54 in muscle, and it's 6 times that in bone. So at low kVp, we get a substantially more higher rate of absorption in bone than what we do in muscle. So we talk about kVp and how kVp can control your contrast by changing your differential absorption, and that's what I wanted to point out on this. As we increase our kVp, granted you're never going to be shooting a finger with this kind of energy, but you notice that at this point basically the absorption coefficient is only 2 times. So at 100 kVp, you notice it's still 3 times, but that's nowhere near what it was down here at 6 times the absorption coefficient, the difference in absorption coefficient between soft tissue and bone. So as kVp goes up, then your differential absorption changes so drastically that you can increase your kVp to a point where you get almost no absorption in the bone, and it becomes the penetration of the bone and the muscle become more similar. So to maximize our contrast, what we have to have is a high rate of absorption in bone as opposed to in soft tissue. And we do that by decreasing our kVp.
You can see that as the X-ray energies go down, the absorption coefficients for bone and for muscle both increase. Okay, so at low energy X-rays, both bone and muscle is better at absorbing X-rays, i.e. it absorbs low energy X-rays much better than it does high energy X-rays, which is kind of what you expect. Also, you can see that at high energy X-rays the difference is fairly minimal, whereas at very low energies bone is very, very good at absorbing X-rays, and therefore you're going to get quite a large difference in contrast here if you use lower energy X-rays. Okay, and you can see from this table how those two absorption coefficients vary with energy of X-rays. Okay, so what causes the X-rays to be absorbed? All right, and that's what we're going to talk about next. Well, there are 3 mechanisms that cause X-rays to be absorbed in tissue or in the body, and these are the 3. All right, now these are described in detail elsewhere. I mean, the photoelectric effects, obviously, we met last year when we were doing quantum mechanics. Pair production, we've met a little tiny bit when we were doing nuclear fusion in stars. Compton scattering we possibly haven't met yet so far. So we're going to describe these three absorption mechanisms for X-rays. So the first one is the photoelectric effect. Now, in terms of medical physics, what happens is this. Okay, it's quite simple really, and it just involves ionization, and it only applies to X-rays of energy less than 100 keV. All right, so the incident X-ray comes into the atom, all right, is incident in this direction, and it interacts with an electron in such a way that the electron absorbs all of the X-ray's energy. So all of the X-ray photons energy, is absorbed. Okay, so the X-ray is completely absorbed by the electron, and that gives it extra energy, and it is actually removed from the atom. In effect, what you've done is you've ionized this atom, okay, in the body. Now that's clearly dangerous because ionization of body tissue is not a good idea, but we need to keep the dose fairly low in order to prevent problems happening from this mechanism. All right, but the photoelectric effect causes an ionization within the atom, and all of the X-ray's energy is absorbed. The X-ray disappears. There is no photon after this interaction. Okay, so that's one way in which the X-rays are absorbed. The second way is what we call Compton scattering, which is almost the same as the photoelectric effect, but in this case, the X-ray photon it interacts with an electron, but not all of the energy is used up. So the electron is still removed, the atom is still ionized, but there's a little bit left over, okay? And that little bit left over is re-emitted as a lower energy photon. All right, so this high energy, high frequency X-ray photon interacts with the electron sufficiently to give the electron enough energy to remove it from the atom, but the X-ray photon has more energy than is needed to do that, and therefore it is re-emitted, the extra energy is re-emitted as a lower energy photon, possibly in ultraviolet, visible, infrared, and so on, further down the electromagnetic spectrum. Okay, now obviously in order to do this rather than the photoelectric effect, the incident X-ray photon must have more energy, and the Compton scattering effect is very prominent in the range 500 keV to 5 MeV, so 500 kilo electron volts to 5 mega electron volts.
Okay, so I think that the speaker is really speaking to therapy doses, because he's going to get into pair production here in a minute, which is really a therapy dose. These interactions also occur at lower energies, so I don't want you to be confused and mistake that all Compton occurs at 500 kVp and above, or 500 kVp to 5 MeV. It does occur at lower energy ranges, but what you need to pull away from this is that the photoelectric effect that he said occurred at 100 kVp or below, and then Compton effect takes over at a higher kVp level, still applies, and that is that at low kVp levels we get a lot of photoelectric effect. So when you make an exposure of, I don't know, let's say an abdomen at 40 kVp, you're not going to get much penetration. Almost everything's going to be absorbed inside of the patient. Photons can undergo Compton scatter primarily, and then absorb inside of the patient as well in the Compton effect. But if you increase your kVp to 120 kVp for that same KUB, then what you're going to create is a lot of Compton. So the physics of diagnostic imaging still apply here, and that is the higher the KVP, the more Compton that you're going to create. Are you going to create photoelectric also? Yeah, as a matter of fact, as you increase your KVP, you get an increase in photoelectric. Just the overall number of photoelectrically absorbed photons increases. But what we get is a substantially higher rate of Compton. So when we say that the PE ratio, the ratio of Comptons to PE, we get an increase in Comptons as KVP goes up, it's still valid. The overall number of photoelectrics does increase as we increase KVP, but the rate of Compton increases so much faster and so much more substantially that the ratio between those two changes, and we get an increase in Compton relative to the number of photoelectrics that we create. And really the reason for that is because our average beam energy is so low. Even at 120 kVp, our average beam energy is only 40 kVp. So if we changed our technique from 90 to 120 kVp, that's pretty substantial. That's a quite a big increase in KVP. But really the average energy goes from 30 to 40, which is not all that substantial. It's not all that significant.